Hi again. I'm going to talk to you today about something I don't normally talk about, and that is the subject of math. And why am I talking about that today? Well, recently I've been trying to gain an understanding or a intuition for the subject of barycentric coordinates. What are they? Well, if you remember from high school or middle school, you'd have some Cartesian coordinates, and you'd usually have something like a y plane and an x plane. And sorry, that's not a straight line, but it was meant to be a straight line. And you have some point out here, and this would be so many over on the x and so many over up on the y. Well, barycentric coordinates are kind of similar to that, but we're finding the coordinates on a triangle. But when you think about it, it's kind of similar. Instead of using an x and a y, we could use a set of vectors. This could be like an A vector or an AB vector. This could be like a AC vector or whatever, this being the A point, this being the B point, and this being the C point up here. So this would be a vector between A and B, a vector between A and C. And to find that point, really, you could just do what you did on that Cartesian plane. You could add one vector to the other. So you're doing like adding an AB position to a AC position, and you're getting that similar result. But let me go back to my little application here, and I apologize if this is not making any sense. But what are barycentric coordinates used for? Well, they're really important in computer graphics because just about anything that has to do with 3D is going to use barycentric coordinates. Whenever you see a shaded polygon in a 3D program, the three corners of the polygon or the triangle are going to be shaded by one kind of shade and one kind of color or another, and you have to have some way of calculating that. Or if you have a texture map, you have to have some way of having a unique coordinate for each little spot on this triangle. Every unique individual spot on this triangle is going to have some unique coordinate. And there's different ways of visualizing this. And there's other things, even in the realm of 3D, that this is used for. For example, interpolating the shading across the triangle is also using barycentric coordinates, or so many other things. I can't even, off the top of my head, I couldn't tell you. But it's good to learn. It's good to have an intuition for how it works. So I wrote this little application. There's some sliders here. You can kind of play with them. And just using the sliders alone is kind of hard to get an intuition of what these are doing, because these parameters they're kind of interdependent on each other. Just changing one of them doesn't really do anything. But if I put one all the way up and one all the way down, you'll see that we have a point over here in the corner. And as we start moving these towards each other, we'll eventually get to the point where we're right in the middle. And you see, if these two are in the middle, this will be right in the middle, and so on. And if you watch this as I move this from one side to the other, you'll see that's what happens. These are kind of the opposite of each other, but that is not intuitive. So I've made some other visual changes, some visual cues here that'll help explain this. So we talked about vectors, and if I go here and you look at the yellow part, and if I move this spot right along the top edge, you'll see there's a one-to-one correspondence between this yellow vector and the little dot there. But if I move this out here, you'll notice they start kind of interacting with each other. Again, if I move this across the bottom um, line, that's a one-to-one correspondence. But if I move it right down the middle, you'll see these are half as long, but they're both moving kind of at the same distance. And if I'm like 2/3 of the way over here, You can see that one's longer and this one's shorter. Well, what's really going on there? What does this mean? Well, as we talked about Cartesian coordinates earlier, um, if I go here, if you look at this and you look where this spot is, you can almost imagine what's going on. You look at this one little yellow line, and if you imagine adding this other yellow line to the end of this line, you'll see exactly what happens. It plots right to this spot here. So I'll show you that. If you go to add vector, this adds this this vector here to this vector here, and it plots directly to that spot. And I'll turn off the original thing there, and you'll see, just like before, there's a one-to-one correspondence between that, and there's a one correspondence to that. But if I move out in the middle, you see this is half as long, and the vector over here that would be half as long has been moved over here, and it now plots right to our center spot. So that's one way of thinking about that, as sort of a vector addition. And as we talked about the Cartesian plane, there's an x and a y. Well, this is sort of like that. You're plotting in one axis, and then you're plotting on another axis. And that's one way to think about it. Another way to think of this is, um, I know some people find this more intuitive and some don't. But as how would you call this? A sum of the uh, areas of these subtriangles. So you have three subtriangles within this big triangle, and each one has a weight, and that weight is derived from the area of the subtriangle divided by the area of the entire triangle, and that's true for each subtriangle. So if you watch this, as I move, if you watch this top parameter right here, as I move this towards the top, you can see that number dwindling as we get to the top of there. It reaches 0. Why? Because there's no more area there. Same if I go down to this bottom corner over here, this middle area here, that number starts to dwindle. Why? Because there's no area there. But if I move it all the way to this side, this number is almost 1. If I get it right in the corner there, it becomes 1. That means that subtriangle um, is the same size as um, the entire triangle, and dividing one by the other will still give you a 1. So that is one way to think of it. So if you need to find a barycentric coordinate from a x and y position, that's one way you can do it. You just you plot that point there, you make these subtriangles, you calculate their area, and you divide those areas by the entire area of the whole triangle, and that will give you those barycentric coordinates. Um, and still on the way of trying to find an intuition of what we're talking about here. If you watch these numbers, um, hmm, it is basically a weight. Basically, um, each of these values, each of these points has a weight associated with it. And if this point is all the way to the red, then that weight will be 1. So you'll say, okay, you multiply red by 1, and you get a fully red value. But if you're down here, there'll be no red, so that red gets multiplied by 0. And actually, that function looks like something like a times the first. Let's see. All right. Well, I think the formula would actually look a little something like this. Got a little help with it from the wiki page or whatever. And to to break this down a bit, P is the point we want to find. P is a vertex, so it would have an x and a y aspect to it. And let me get a slightly smaller brush here. It's kind of hanging me up using a big fat pen like that. So I'll use a smaller pen. So P is a point that we want to find, and P will have an X and a Y. Sorry, it's kind of hard to draw that, but W, U, and V are like coordinates, like UV coordinates. Um, and a W is a third coordinate that we'll find. So remember, we have this triangle with some lines, vectors between them, or whatever. We want to find the coordinates, say this is U and this is V. Then W would just be the one over on this side that we can extract from these other two if we need it. Um, or you could think of U and V as the weight of, also you could think of it as the weight at these points. So, um, so A, B, and C are the vertices at that form the points of the triangle itself. So it would be A, that would be B, and that would be C. So what we're trying to find is this point here, somewhere in the middle. That would be our P. Sorry, it's trying to make a P there. And best I could do. So all you have to do is multiply, let's see, V times B. I probably did all this wrong, but somewhere along those lines, you have to multiply the weights by the vertices, and that will give you the point. So um, that's not helping, I know, but that is basic. Whoops, whoops again. That is basically the formula. If you think about it, if you multiply this point by a weight, and this point by a weight, and this point by a weight, and you add those together, then you'll get some average between them. The one thing we have to remember is all these U, V, and W's together have to add up to 1. All right, meaning it's normalized. All right, so going back to our little application here, turn this off for a second. Like I said, if the weight of this point is all the way over here, then we'll get this point ending up over in that corner. If the weight is all the way over here, we'll end up all the way over there. And if the weight's all the way over here, we'll end up down there. But if the weight is some value, 1/3 of each, then we'll end up right in the middle. And if we put that right there, you'll see the value of these are almost exactly 1/3 each. Or if it's halfway between two of these, then one will be all the way up and the other will be all the way down, like you see there. Or, yeah, I did that wrong. No, if it's halfway there, then two of these will be 50/50 and one will be all the way down. And that'll be the same for over here. Two will be 50/50 and one will be all the way down, and the same for over here. If it's right in the middle. So I don't know if any of this is helping, but I found it interesting, and going through it a bunch of times has helped me get an intuition for it. And what we did here with this point, with this triangle, is um, on the U point we made that red. On the green, on the V point we made that green. On the W point we made that blue. So wherever here gets where the weight is all to the red, it's all shaded red. Wherever and in the middle you get a shading of everything mixed together. So I don't know if any of that's helpful, different ways of thinking about barycentric coordinates. I don't know if it's interesting, but I found it interesting. But thanks for watching and talk to you later.